The next type of method that we're going to talk about for doing probability problems is called hypergeometric. And it's important to understand the difference as to when to use hypergeometric. So the fundamental counting principle is when you know the probability of each piece of the arrangement. For instance, if we were to get 3 cards in a row, one at a time, that's important, one at a time, from the deck of cards, and without replacement, so they don't go back in the deck, then we could figure out the chance that the first is a ace, the second is an ace, the third is an ace. We could also have done that problem using permutation, and so that emphasizes the fact that we're talking about arrangement. We use a binomial or multinomial method of determining probability when the probability is never changed, so they're independent. In other words, if I'm a 10% foul shot shooter, even if I make 10 foul shots in a row, the assumption is that I am still a 10% foul shot shooter. Also, it'll always be something of the nature of, what's the chance that I make 3 of the next 5, where you don't necessarily know what's going to happen in my first shot or my second shot. You just know 3 of the 5 will be made somewhere along the line. The hypergeometric is made when you are drawing several cards from a deck of cards, several seeds from a packet of seeds, where there's a limited supply. There's only 52 cards, or the packet of seeds only has 100 seeds in it. And you want a certain outcome, and you've drawn the seeds all at once. So not one at a time where you're looking at it, or the cards. And the probabilities, in effect, sort of change because you're drawing down from a total. So here's a question. You're dealt 5 cards all at the same time. You don't know which one's first, second, third. Here's just your 5 cards. You turn them over, look at them. What's the probability that there's 2 aces? At least 2 aces. 3 of a kind. Now, it could be 3 eights, 3 sixes, 3 kings, and a full house. Now, what a full house is in poker is you have 3 of one type of card, like 3 queens, and then 2 of another type of card, like 2 eights. That's a full house. Now, in this method, it's basically the good ways over the total ways. And this is maybe a method that you were first introduced to probability, good over total. The good ways here for 2 aces is that I have to get 2 of the 4 aces. So of the 4 aces, pick 2 of them. And of the 48 cards in the deck that are not aces, we must pick 3 of them. That's how we're going to end up good. And the total ways we can pick the 5 cards is 52 cards, pick 5. So good over total. In the next one, I'm doing complementary counting. So I'm taking a 100% chance that something is going to happen. Minus out the ways that's the opposite of this question. At least 2 aces. 2, 3, or 4 aces. So take away the chance of no aces, or take away the chance of 1 ace. So no aces and 5 other cards for 1 ace and 4 other cards over the total. In these last 2 questions, if I'm going to get 3 of a kind, first, of the 13 different kinds of cards in the deck, ace, 2, 3, 4, 5, all the way up to king, I got to pick one of those types of cards. Then I've got to pick 3 of the 4 of that type. And then I've got to pick 2 of the remaining 48 cards that are not whatever type of card this is. So pick a king, pick 3 of the 4 kings, pick 2 cards that aren't kings over the total. For a full house, of the 13 types of cards, I got to pick one of them, king. Now I'll get 3 of the kings. Now I'll pick one of the remaining 12 types, 8. And I'll pick 2 of those, 2 eights, over the total. Our next type of probability is property of inclusion and exclusion. So we'll say that 60% of students take the bus to school, 70% of students play a sport, at least one sport, and we're going to say that this is independent. In other words, you are just as likely to play a sport whether you take the bus or not. There's no influence of taking the bus on whether you play a sport. Those are separate things completely. What is the probability that if I pick a random student, that student does either takes the bus or plays a sport or does both? Notice that there's only one event here. I'm picking a student. What's the chance that student does one or the other or both? We'll start by calling this first group of students set A, this second group of students set B, making a Venn diagram, putting my 0.42 in the middle. I know it's 0.42 because if it's independent, then I can multiply these two individual probabilities to get A and B. A and B equals the first probability times the second probability. Then I can put the remainder of 0.6 over here and the remainder of 0.7 over here. And when I add these all up, they only add up to 0.9, actually 0.88, 0.88. So the remaining up to 100% has to go in, this would be the group of students who does neither of these things. So A or B, that would be the probability of A plus B minus the double counting that's in the middle of A and B. There are a couple other questions I could ask. What's the probability of not A or B? And that line over the top is not. So figure out A or B and subtract it from 100%, not A or B. Or the probability that it's not A or B. So they don't take the bus or they play a sport. So probability they don't take the bus plus probability that they play a sport minus the probability of the overlap of those two. And this is just a complement of A is here. Here are a couple questions having to do with independence and Venn diagrams. If given this information, is it independent and can you draw the Venn diagram? The first one's pretty straightforward. It's not independent because when I multiply probability of A times probability of B, it must equal the probability of A and B, and it does not. Also the Venn diagram, pretty straightforward. The overlap, 0.2 is in the middle, and I need what's left to add up to 0.7, and I need what's left in B to add up to 0.4, 0.4, 0.7, and this all together is 0.9, so there's a 0.1 on the outside. The second one, not nearly as straightforward. Independent. Well, I don't have the right pieces parts, so I can't really tell right now. So I'm going to draw my Venn diagram first. If it's not in A or B, not in A or B or both, that's 0.2, so that's the first thing I can put. The second thing I can put is the 0.2 right here, because if it's not in B, it's 0.4. Well, not in B will include this stuff out here and this stuff in here, so that adds that to 0.4. The third thing I can put is the 0.1 right in the middle, because I know probability of A is 0.3, so that adds to 0.3. Finally, the last thing I can put is the 0.5 right here, because everything must add up to 100%. And now I'm ready to determine whether we have independence. Probability of A and B, there's the middle, and that has to equal to the probability of everything that's in A times the probability of everything that's in B, and it does not. Another question that can be asked is to write the description for the shaded part in the Venn diagram. So what is this part right here? Here's a couple strategies. In the first case, we could try to say it in words. The shading here is in circle A, but not in B, or not in that part of circle A that's also in B. Or we could say, well, the shading is definitely not in circle B, but it is in circle A at the same time. So that could help us. It's in A and not B, or not B and A. In the second picture, a different strategy is I've made all this yellow shading, and if I take only the yellow shading that is in circle C, then I'll have my final answer. So how can I describe the yellow shading? And then how can I say, and it has to be in C as well? And in this case, the yellow shading is, as opposed to this one that was and, it's going to use an or. So it's definitely all in circle A, or it could also be anywhere else that's not in circle B. So if it's in A, it's good. If If it's not in circle B, it's good. If it's in both of those things, it's good. Now, of all that yellow shading, I only want that portion of the yellow shading that is also in circle C. C and that.